Hello everyone, it's nice to see you on our webinar series which we already started and where we would like to present you some findings from our end as well as our valued collaborators and partners. Before we begin, I would like to remind you that you are in listen-only mode and won't be able to talk, but you can ask our presenter as well as myself question, just type in the question box. And also I would like to remind you that the webinar will be recorded and the link for the recording will be shared with you probably tomorrow. Before we begin, I would like to ask you whether you can hear me well. So could you please type in the chat or in the question that you can hear me and see my screen? Okay, great. So let me begin with just a quick introduction of what Chemspace is and what we're doing. So Chemspace is a marketplace that connects customers and the suppliers, and the idea behind the platform is to have a single place for ordering compounds. Currently, we have the largest collection of the largest catalog of the compounds like building blocks, screening compounds, and fragments, and that includes over 330,000 in stock building blocks, almost 6 million in stock screening compounds. All the compounds are focused on medicinal chemistry and pharma research, and can be easily followed up with billions of make-on-demand analogs that we also offer in our catalog. Those analogs are based on thoroughly documented synthetic protocols from trusted suppliers, and they are indeed delivered with high success rate. The Chemspace catalog is available online. You can go to chemspace.com/search and do the pretty fast search in almost 1.6 billion items. It's available through API integration with a client application, and it's available through integration with ERP through Punch-Out. And yes, we have this probably the largest catalog available to search and purchase from us, and we do understand that the most important is the application of the compounds that we have. For that, we established a few collaborations, and today I would like to introduce you to one of the collaborations we have, and that's basically collaboration with Iktos. And let me introduce Dr. Quentin Perron, the co-founder and CSO of Iktos, who will be presenting today the retrosynthesis in the AI era, opportunities and pitfalls. So Quentin received his PhD from University of Geneva. He did a postdoc at UCLA and had a few positions prior to founding Iktos. With that, I would like to basically to let Quentin present his talk now. Just
right, can you see my screen? Yurii?
Yes, yes, I can see my screen. Yeah. And I hope everyone as well.
Okay, in full screen now?
Yes.
That's great. Thank you very much, Yurii, for your kind introduction. And you're right. Today the topic is AI for retrosynthesis. A few words about Iktos. We are a startup company based in Paris, incorporated in late October 16. We have our headquarters in Paris, and we have also some Iktos Inc. in US, based in San Diego. We are a specialized startup in the field of AI applied to chemistry, where we use this AI technology for generative models. So it's de novo drug design, and for data-driven retrosynthesis. We are working with a lot of companies from mid-size to big pharma on different type of project, from hit discovery, lead optimization, late-stage lead optimization, patent busting, ligand-based or structure-based projects. So we have several business models, service mode, research collaboration and softwares, Micah for de novo design, and Spaya for retrosynthesis analysis, which is the topic of today. So, you know, the retrosynthesis, the concept is quite simple. You have a molecule you want to make, and you have to break it into pieces until you end up to commercially available starting material. There are many challenges to have this work be done by a computer, because you have to explore a huge number of possibilities in a reasonable time frame and computational cost. And also, when you break a molecule into pieces, you have to make sure that the two daughter molecule, I would say, are going to react together at the proper place. So the question is, can we do that? Is it too complex? Scientists has this question also for chess or for AlphaGo, and in this both field, AI and machine learning have been proven to be as good as human, even better. So we try to achieve such results in retrosynthesis. We are not the only company working in that field. There are the only research group. Many scientists work in that field since many years. As you may imagine, it's a very complex field, and we try to bring our science, our technology to improve this difficult task, to have a machine which is able to perform retrosynthesis. There are two main approaches today: the expert-based method, where chemists, chemoinformatics encode rules by hand, trying to understand the reactive center, the context of a reaction, and you have the data-driven approach, where you have an algorithm which extracts by itself the chemistry from a database of reaction, which is actually where we are working. To perform such algorithm, you need a database of reaction to train your algorithm to learn chemistry. You need a database of starting material to stop your algorithm during the retrosynthetic analysis, and you need an algorithm. The algorithm is composed of three main pieces. The first one is how to cut the molecule into pieces, so it's a disconnection prediction. And once you have cut the molecules into several pieces, you have to make sure that those pieces are going to react properly. So you need a second algorithm, which is reaction feasibility. And then you need a search strategy, a search algorithm, because you can break the molecule into several pieces and each daughter molecules into several pieces as well. So rapidly, your tree of research can be enormous. So you have to navigate intelligently in that tree. And of course, this technology is for chemists, and you need a chemist or computational chemist, and for that you need an interface to play with the results. So first, disconnection prediction. So the disconnection prediction is an algorithm where you input the molecules and the output is a number of different reactants. Several ways to tackle that problem: the template-based method, where you have to predict the templates. You apply the templates and you break the molecule into pieces. We will have a look how it looks like a template. And you have the template-free method, where this is more an algorithm which is like translation algorithm, where you input something and it directly outputs the reactant without predicting something else like a template. So like Google, translate, you enter a word, and the output is another word in another language. So for the disconnection prediction, a template actually it's a regular expression, like carbon nitrogen become carbon bromine plus nitrogen. And if I apply this regex, which is compatible with the smiles of this compound, which is ranolazine, I obtain those two daughter molecules. This is actually what is a template, a simple regex. How do we extract templates? Templates is coming from reaction, and a reaction comes from providers, public databases, or ELN, and a reaction can be encoded into a smart reaction. Smiles, dot smiles, arrow, give a smile. So this is this reaction encoded into a smiles reaction. From this smiles reaction, we can extract a template, but first, very often the raw reaction is quite dirty. You have catalysts, you have reagent, reactant, solvent, sometimes on reactant position, sometimes on the product position, and all those reactant, reagent, solvent can interfere with the atom mapping step. So you have to clean that. We have work hard to have a full automatic pipeline which is able to properly clean those reactions. Once you have a clean reaction, you can perform atom mapping, which allow to localize atom on the reactant, atom on the product, and to be able to localize where things has moved, change. And here we can see that between carbon 2 and nitrogen 11, the triple bond has become a single bond. We reverse this template and we have a retro rule saying that a carbon single bond nitrogen can come from a carbon triple bond nitrogen. So we perform the data preparation on Pistachio database, which is provided by Nextmove Software, a company based in UK, where they extract automatically the data from European patents and also US patent. So there are a lot of duplicates because people who are patent reaction in US do also patent those same reaction in Europe. But once we have cleaned and deduplicated this database, we have 3.5 clean millions reaction. Then we perform the atom mapping and we extract 2.8 million reactions. So 80% of the database of those reactions has been extracted, which is quite a good number. The remaining percentage is sometimes an extraction which has not been done properly, and the atom mapping did not work well, so the reaction has been thrown away. So then once the database is clean, we have reactions, we have rules, and associated templates. Then for a given product, we have to train a neural network to predict, seeing that product, which type of retro rule ID it can propose. So we train an algorithm by providing to the system the product, so a fingerprint, and it has to predict, it's a multi-classification problem, it has to predict an array of more than 60,000 templates. 62 exactly. So it's a feed-forward architecture where you have the product Morgan fingerprints, several hidden layers, and the output of 62 templates for a given product. You take the top 51 and it gives you an accuracy of 95%, meaning that you give a product, the algorithm predicts top 50 templates, and within those top 50, you have 95% chance to find the one which is described in the literature. Then reaction feasibility. Once you have break your molecule into pieces, you have to make sure that those two pieces are going to react together. For instance, same example, I take the ranolazine, the top one retro ID says that oxygen plus somewhere in the molecules carbon nitrogen become carbon oxygen plus somewhere nitrogen. So if I apply this top one rule ID retro on ranolazine, I obtain that two daughter molecules, which looks great actually. But also you have other places where you have oxygen, other places where you have carbon nitrogen. So if you apply this template everywhere on that molecules, you can also obtain this kind of crazy disconnection that we don't want to see. because they are just not real disconnection for a chemist. So you have to get rid of those disconnection. Also, if I want to prepare that compound, maybe the algorithm can tell me that in the 10th position, retro rule 94 proposes a Friedel Crafts reaction. Maybe it's a good idea, maybe it's not, because if I go to the lab and I'm trying to do the Friedel Crafts on this indole, I may have a lot of retroisomers. So it's maybe not a good idea to propose that retro rule. So you have to remove it in a way. So for that, you have different solutions. One of the is to have a model which is able to tell if a reaction, so product, starting material, is something which makes sense. So will it work, yes or no? For that, you have feasibility classifier, which is proposed by, for instance, Marvin Ziegler in his paper, where he built a database of true reaction, which are the reaction from the initial data set, and plus he created false reaction by combination of starting material and templates. And then he trained models trying to predict and to distinguish true reaction versus false one. You have another approach, which is proposed, for instance, by Alphali from IBM Research, where they have starting material, and from this starting material, using molecular transformers, they try to predict the product. If the product is identical to the one you are looking for, it means that this disconnection makes sense. At Iktos, we have split this difficulty into two different algorithms. One, we call it applicability domain estimation, where we try to understand if the disconnection and the crazy disconnection are make sense or not. And the second one is a dedicated radioselectivity filter, which is an AI algorithm which enter into the game if it detects possibilities of radioselectivity issue. And so I won't going through the detail of those algorithms, because this part of the algorithm is something proprietary and quite important to have to output good results in this type of technologies. But just to give you a flavor, this is screenshots of in-house application we have to debug Spaya, and we can see that this, for instance, disconnections is passing our applicability domain estimator, where all those disconnections are not passing the applicability domain estimator. Also, the radioselectivity filter, for instance, if we provide it this reaction, it will give a probability of 0.48, which tells us that this reaction is not a good idea. Also, what about chemoselectivity? Chemoselectivity is something very important and very hard actually to tackle, because, for instance, if I want to prepare that compound, if I put only one equivalent of Grignard, it won't work, because the Grignard gonna be quenched on the acid moiety. If I put two equivalents, it's gonna work. And very often we don't have this type of information in the database we have. So that's why it's very difficult task to deal with chemoselectivity. Also, it's depending sometimes from solvent, temperatures. So some reaction which work at 0 degree maybe don't work at -20 or things like that. So chemoselectivity is not an easy one. One way to tackle that is, again, to take those two starting material and to try to see how we can predict the output. Today, Alphali demonstrate that the best way to do that is molecular transformer, and he claims that you have a 90% accuracy for the top one prediction, and this is actually true, but only if you have two reactants, or at least two reactants on this part of the reaction. If you have only one reactant, the accuracy dramatically drops. And in Pistachio database, for instance, we have half multi-component reaction, half mono-reactant reaction, and in that case, we have a 66% accuracy of the top one prediction. So we cannot use this in production. Because, for instance, if I provide this to the algorithm, it can propose, you know, directly the acid saying that the greenhouse has been quenched, also the product we are expecting, but not necessarily at the right probability, or maybe very flat probability. So it's not very useful. Also, this type of technology are working on GPU, which complexify the architecture, and it's quite slow. And for retrosynthesis, we want to be very fast. But nevertheless, we have observed that chemoselectivity can be partially tackled by if you have a good prediction disconnector. Because, for instance, if I want to prepare that compound, we arrive on a step where the algorithm sees this compound and still propose the condensation of the greenhouse on that compound. And we can say, okay, maybe we're going to have issue of, you know, chemoselectivity. We have an aldehyde, a keton, an ester. But actually, this is not a bad idea, because if you see the most similar reaction into the initial data set, you have this reaction. And it's possible actually to add a greenhouse to that compound without having, you know, chemoselectivity issue. And if you have a look to the protocol, you have one equivalent of greenhouse and one equivalent of this aldehyde. So that makes sense. And so the prediction disconnection models is able to understand that as well. Also, another way to overcome this issue is to introduce protecting group. And for instance, this is also done by the prediction disconnection. Because if I want to make that compound, one of the biggest probability is not to come from a keton reduction, but it's first to introduce an acetyl moiety, a protecting group. Because here you can see that the probability is 0.9, where the direct reduction of the keton is very, very low. So this is also partially taken into account by the prediction disconnection. So combining, so if you have a good model of prediction disconnection, you partially overcome chemoselectivity issue by introduction of protecting group, for instance. Also, we believe that Spaya is not perfect, and we have on the public platform allow users to dislike disconnection if they think that the proposed disconnection won't work into the lab. So this provides us some feedback. But also, when you have a retrosynthesis you like, you can save the root, and by saving the root, you indirectly tell us that the disconnection are making sense, which is also important for us. So we have a disconnection prediction, we have reaction feasibility. Now we have to search our path in these infinite possible disconnections. So to do that, we are using reinforcement learning, which is actually like Pac-Man, game. You are evolving in a maze. You have to take actions in a given environment where you have monsters, rewards, and based on this, the states you are, so the position you are and the reward you are, you have to take decision and actions. So this is, reinforcement learning. I won't dive into the technology because I think it would take a lot of time, but what I want to say on that aspect is we are orchestrating this reinforcement learning through a Monte Carlo tree search algorithm. And we are, one particularity at Iktos is that this Monte Carlo tree search algorithm, this MCTS, has memory. It is directly and strongly coupled with the database. So, for instance, a retrosynthesis which is not working today can work tomorrow if maybe someone put a given intermediate. So the algorithm will take advantage of the past retrosynthesis. So we are not waiting for users to fill this database. We have already performed the retrosynthesis of the full Campbell. And now the algorithm has some ideas when you put the new molecules where to go in these infinite possibilities, because your molecules is maybe similar to something has already retrosynthesized. So it's allow the algorithm to be really fast, actually. and to propose highly diverse solutions. And finally, you need an interface to play with the results. So it's not very easy to display trees of retrosynthesis. You have several ways to do it. We decided to work more or less than a Google search, where we provide results in the fly, in live, and we run them using a score, where the higher the better. So the score, if it's 1, it means that it's an exact literature match. So Spaya has been able to retrieve actually a published retrosynthesis. If the score is different than 1, the higher the better. It takes into account the probability of the models, our applicability domain estimators, the number of steps. You know, the shorter the route is, the higher the score is, and also how the molecules has been broken into pieces, or how convergent the route is, and which allow to rank all those routes. Also, when you have many routes, we like to cluster those routes by the first retro disconnection or the last reaction of the forward synthesis. And here, for instance, ranolazine, you can see that the first disconnection, which is proposed by the algorithm, is this one, which is actually reacting, you know, that secondary amine on the allyl derivative, and it occurs in that position. So this could be an interesting route if you want to introduce diversity here, for instance, or if you want to introduce diversity in that position, we would advise to have a look to the routes where the first retrosynthesis step is this one, which occurs on the other nitrogen by condensing this secondary amine to this amide. And you have a lot of, you know, possible first retrosynthesis disconnection. Maybe I will have a look rapidly to the Spaya offer, because, you know, the first things we can propose with such technology is to propose an interface where you input the smiles or draw molecules, and you have a lot of solution, and you can browse the solution, save your tree, and print a PDF, and, you know, go to the lab and make the reaction. But also, and this technology again is available on Spaya.ai. But also, we are working on Spaya Advanced Search, which is going to be released early October, where you input the smiles, and you can also input an intermediate, and you will force the algorithm to perform the retrosynthesis, where you have this intermediate into the roots. And this is highly valuable for, you know, chemists who has, let's say, you know, 10 grams of this intermediate. They don't want to see a route if it's not passing by this intermediate, because they just want to consume this intermediate. And so this is doable soon in Spaya, and also to limit the search by a certain number of steps, not afterwards, which is available today, but during the retrosynthesis research. Also limits the price of the starting material. We are working on it as well. We have also developed Spaya API. The beta version is available. This is more for computational chemists who don't really want to see the routes in detail, but they just want a score for given molecules. So you just put some batch of smiles, send it through the API. We score by our AI score and the number of steps of the shortest routes, and we send it back to you. It takes something like 3 seconds per molecules per worker. A worker is, you know, the technology we have developed containing MCTS and all the package. It requires 6 CPU. So the technology is currently implemented in AWS, and with 250 CPU, you can run 50,000 molecules per hour. We also made some tests, and without any issue, we can run 200,000 molecules per hour using 100 CPUs. You know, you can instantiate in a minute those type of, you know, those CPU. So this technology is in production. Just ask us if you want to have access and to try it. We have also this Spaya API can be connected to generative models. The concept is a bit different because if you generate using batch of 256 miles, for instance, you have to wait for that the slowest molecules has finished before putting back before rewarding your generative models. So it's slow down a bit the process, but you can easily generate 100,000 molecules within your reinforcement learning process, for instance, branch to our API of retrosynthesis in less than 10 hours. We have also developed Spaya batch retrosynthesis. You have a series of 100 similar compounds, and you want to make those compounds in the minimum synthetic effort. So you are looking for key intermediates. So Spaya will try to find key intermediates to prepare that compound, to prepare 100 compound in maybe 105 ideally steps, meaning 5 steps for the advanced intermediate and 100 steps to prepare 100 compounds. So this is basically the idea, to find advanced intermediates to prepare a set of compounds. So this technology has been validated in our R&D department, and we are currently working on the user interface. So Spaya is totally customizable, easily can be easily implemented in your private cloud if you want, highly scalable. Also, we believe that this technology can be highly powerful if it's connected to your starting material, preferred partners and providers. But also, we believe that taking advantage of your chemistry, which can be highly specific, it can be also very interesting. So we can, in less than a week, create a dedicated Spaya, a tailor-made Spaya based on your starting material, but also on your ELN database, and taking advantage of your chemistry. So feel free to have a look to Spaya. I will just make a short demo since we are right on time. But it's freely available again on spaya.com. Thank you very much for your attention, and I will switch to the demo right now. So, you just have to type Spaya on Google, and we arrive on the first position. Just click on the link and log in by providing your email and a password, and you will receive a link to have access to the platform. So you can, for instance, enter a smiles, or if you want, draw a smiles. Draw molecules. It's up to you. Then you click on done, and the algorithm will look for roots to this compound, which is a very well-known compound, imatinib. We have, as you can see, a lot of clusters which are proposed, which is the last disconnection, several ways to tackle the synthesis of that compound, as you can see. As you can see, also the score is descending by this cluster, and each score is the top score of a given cluster. And the lower, the worse, I would say, with less probability and higher number of steps. So I advise you to have a look to the top score. If I click on a cluster, I have several propositions with several different types of starting matter, but still ending by the same, the same steps. So the same first retrosynthesis steps, but with different type of starting material and strategies. Okay, so if I, for instance, click on the first cluster, I see here this is an exact literature match, so I can click on it, and I have an exact literature match reaction. I can have a look on the most similar reaction. As you can see, this is one which has been published here, but I can have a look to a bit different reaction where you have modification on the molecules, the similarity is a bit dropping, but which is interesting here is that you have the protocol. And you can also, of course, click on the link to the patent and be redirected to Google. If you like these routes and you think it's enough for you, you can of course save it. If you think that you are not very comfortable with that compound because it's too expensive, you can ask the algorithm to find routes to that compound. I can see that I'm lucky because that compound can also be made by something which is known into the literatures. For instance, this proposition, I have a look and it's right. It has been already published. But as you can see here, I don't have any protocol. But here I have a protocol, so maybe I will prefer this procedure. So I will pin that literatures and that protocol, and so that when I will print it, I will have access. And this is only that which going to be printed. But if I like this one as well, I can also pin this one. So if I am happy with that tree, I can of course change it if I want. I just have to save the change, generate a PDF, and rapidly you have access to your PDF, and you can of course then print it and go to the lab and work on that retrosynthesis. As you can see, this reaction, this is the one proposed by Spaya. This is the one which has been published. We have the yield, the time, the protocol, the reference, and the same on this one. And this is the other steps with, again, the reference and the protocol. So here you have your retrosynthesis you have saved, your recent search. I think this is more or less what I can show you today. Just maybe to finish, as you can see, there are a lot of results. If you think you have too many results, you can of course limit the number of steps and see the retrosynthesis in one step, for instance. And also, if there are things you don't like at a certain level of the tree, you can of course at any time click on more routes from here, and the algorithm will propose you alternatives routes starting from that point. So feel free to have a look, to test the technology, to provide us your feedback. Again, Spaya is the beta version. We're gonna implement very soon the advanced search, and also an environment here in my retrosynthesis where you will be able to share retrosynthesis with your team in order to work on some projects in a collaborative manner. So keep posted, and we'll let you know all those new features are coming very fast. So keep posted. Thank you very much for your kind attention, and happy to take questions.
Thank you, Quentin, for this kind presentation. So if you have any questions, please type them into the questions bar, and yeah, we'll answer to them. Let's wait more. Okay, so here's the first question. Could you please give more information, if possible, on the development of the search engine for Spaya?
Yeah, so we have done another webinar, I think something like 1 month or 2 months ago. So if you browse Spaya retrosynthesis on YouTube, you will have access to that, where we have more focus on the search algorithm. And this search algorithm is presented by Hamza Tajmouati, who is the lead scientist on Spaya, and you will have no better description that can I do because I'm an organic chemist. But basically, it's Monte Carlo research through reinforcement learning, similar to what has been, for instance, published by Marvin Siegler. But of course, we have developed a different way to orchestrate it. And also, as I was explaining, the particularity of our algorithm is very, strongly coupled with the database, which changed a bit the way to explore the possibilities of this algorithm. So we believe this is something very important to have an algorithm which goes very fast, but rapidity is something important, but also for chemists, strategies and diversity of the disconnection, it's also something very important. And we believe that for having such level of diversity, using a database is something very, very nice to have at the same time diversity, exploration, exploitation in a reasonable computational cost and time.
Thank you, Quentin. I think what we can do, we can also share the link, to this webinar of yours, so people can get more insight if they're interested.
Sure.
Any other questions? Okay, if there are no questions at the moment, I think I would like to thank everyone for attending the webinar. And as I said, the webinar recording will be available probably tomorrow. We'll share it with you via email. And if you have any other follow-up questions to Quentin or to myself, feel free to contact us. Thank you again, Quentin, and thank you, everyone. Stay safe.
Thank you, Yurii. Thank you, everyone. Bye-bye.
Bye-bye.